For decades, civil engineering has relied on intense manual labor. Look at any major skyline, and the buildings were likely constructed through a slow, deliberate process of human hands placing materials piece by piece, much as we did a century ago. That traditional approach relies heavily on physical formwork, massive wooden or metal molds built just to hold the liquid concrete until it cures. Those are only where it is strictly required. By eliminating the need for temporary molds, the process drives material waste down to nearly zero. This chart illustrates that efficiency jump in real terms. While conventional methods yield about 0.9 units per hour, automated 3D printing output can reach 13.79 units per hour, a productivity increase of over 14 times. At this scale, meeting the sheer volume of current global infrastructure demand is no longer feasible using manual labor alone. This technology is already operating on construction sites. Entire communities are printed from the ground up, delivering structurally complete homes in a fraction of the usual time. The applications stretch well beyond simple walls. This 3D printed steel pedestrian bridge spans a canal, demonstrating that the technology can handle the complex geometries and load-bearing requirements of public infrastructure. But the hardware is advancing much faster than building codes. Regulatory agencies and legal frameworks are struggling to adopt to a process bypassing established safety standards. If a machine extrudes a finished building in 48 hours without traditional rebar or internal masonry, building inspectors lose their usual methods for verifying the structural integrity of the walls. Until engineers can provide a consistent way to verify the strength of a printed wall, the technology remains a specialized alternative rather than a global standard. If an inspector can't sign off on a building by looking at its frame, the safety verification has to come from the inside. This is why we are seeing a shift toward digital twins, replicating the physical structure in a live digital environment that updates as the building ages. Researchers at the Government College of Engineering, Ratnagiri, and the Rajaram Bapu Institute of Technology are leading a breakthrough in this area. They are pioneering AI-based structural health monitoring to solve the verification problem. The physical process involves embedding internet-connected sensors, specifically accelerometers and strain gauges, directly into the 3D printed material as the structure is being built. These embedded sensors track temperature shifts and load fluctuations, listening for the exact vibrational patterns that indicate microscopic fractures forming deep within the concrete. By weaving this hardware into the walls, a standard concrete shell is upgraded into a smart structure equipped with a digital nervous system, capable of actively reporting its own physical stress. Gathering thousands of data points a second creates a massive stream of information, which is useless without a processing system capable of interpreting it. LSTM networks take chaotic vibration signals and organize them to learn the building's normal rhythm. This structured data then passes to support vector machines. A clear line separates the output, classifying the building's status into a safe or anomaly zone. Working together, these algorithms identify tiny frequency shifts and predict material fatigue well before a physical crack ever appears on the surface. By moving infrastructure maintenance from physical, reactive inspections to digital, proactive predictions, this AI framework provides the continuous proof of safety that regulators need to approve automated construction. The integration of automated building and AI analysis starts before a single wall goes up. Machine learning algorithms are used early on to optimize the exact chemical mix of low-carbon geopolymer cements for maximum strength. The moment the structure is rapidly printed and the material sets, the embedded monitoring network comes online to protect the asset for its entire operational lifespan. This reality updates the civil engineer's job. Heavy scaffolding and flat blueprints are making way for robotic gantry systems, edge computing, and neural networks. As urban populations swell globally, combining high-speed automated construction with continuous structural monitoring gives us the tools to expand housing and infrastructure safely and affordably. The future of human infrastructure relies on this dual approach, building our physical world layer by layer while protecting it bite by bite.